Performance task number 8 by Jasper Isiderio of PSEC3A. So, first is the slot antenna. A slot antenna consists of small metal surface, usually flat plate, with one or more holes or slots cut out. When the plate is driven as an antenna by an applied radio frequency current, the slot radiates electromagnetic waves in a way similar to a dipole antenna. The shape and size of the slot as well as the driving frequency determine the radiation pattern. Slot antennas are usually used at UHF or ultra high frequency and microwave frequencies at which wavelengths are small enough that the plate slot are conveniently small. At these frequencies, the radio waves are often conducted by a waveguide, and the antenna consists of slots in the waveguide. This is called a slotted waveguide antenna. Multiple slots act as a direct array antenna and can emit a narrow fan-shaped beam of microwaves. They are used in standard laboratory microwave sources used for research, UHF television transmitting antennas, antennas on missiles and aircraft, sector antennas for cellular base stations, and particularly marine radar antennas. The slot antenna's main advantages are its size, design simplicity, and convenient adaptation to mass production using either waveguide or PC board technology. So right here is an X-band slotted waveguide marine radar antenna on ship ranging from 8 to 12 GHz. The antenna radiates a narrow vertical fan-shaped beam of microwaves, scanning the entire 360 water surface around the ship with each rotation. Next, here is a cross-section similar to a marine radar antenna with part of plastic random removed showing slots in the waveguide. So this is what the inside looks like. So there are two widely used types of slot antenna. First is the longitudinal slot waveguide antenna and the transverse slotted waveguide antenna. So first is of course longitudinal slotted waveguide antenna having a slot axis parallel to the axis of the waveguide. This has a radiation pattern similar to a collinear dipole antenna and is usually mounted vertically. The radiation pattern is almost omnidirectional in the horizontal plane perpendicular to the antenna over the 180 degrees azimuth in front of the slot, but narrow in the vertical plane with the vertical gain increasing approximately in 3 decibels with each doubling of the number of slots. The radiation is horizontally polarized. It is used for vertical omnidirectional transmitting antennas for UHF television stations. For broadcasting, a cylindrical or semicircular waveguide is sometimes used with several columns of slots cut in different sides to give an omnidirectional 360 degrees radiation pattern. Next is the transverse slotted waveguide antenna. The slots are almost perpendicular to the axis of the waveguide but skewed at a small angle with alternate slots skewed at opposite angles. This radiates a dipole pattern in the plane perpendicular to the antenna and a very sharp beam in the antenna's plane. Next is disc cone antenna. A disc cone antenna is a version of a biconical antenna in which one of the cones is replaced by a disc. It is usually mounted vertically with the disc at the top and the cone beneath. It is omnidirectional, vertically polarized, and with gain similar to a dipole. It is exceptionally wideband, offering a frequency range ratio up to approximately 10 to 1. The radiation pattern in the vertical plane is quite narrow, making its sensitivity highest in the direction of the horizon and rather less for signals coming from relatively close by. The disc cone antenna has a useful frequency range of at least 10 to 1. When employed as a transmitting antenna, it is often less efficient than antenna designed for a more limited frequency range. SWR or standing wave ratio is typically 1.5 to 1 or less over several octaves of frequency. A disc cone antenna consists of 3 main parts: the disc, the cone, and the insulator. So the disc should have an overall diameter of 0.7 times a quarter wavelength of the antenna's lowest frequency. The antenna's feed point is at the center of the disc. It is usually fed with a 50 ohm coaxial cable with the center conductor connected to the disc and the outer conductor to the cone. Next is of course the cone. The length of the cone should be a quarter wavelength of the antenna's lowest operating frequency. The cone angle is generally from 25 to 40 degrees. Last but not the least is of course the insulator. The disc and the cone must be separated by an insulator. the dimension of which determines some of the antenna's properties, especially on its near high frequency limit. Next is of course the applications. The disco's wideband coverage makes it attractive in commercial, military, amateur radio, and radio scanner applications. Its inherent wideband nature permits it to broadcast undesirable spurious emissions from faulty or improperly filtered transmitters. And number 3 is the lens antenna. A lens antenna is a microwave antenna that uses a shaped piece of microwave transparent material to bend and focus the radio waves by refraction, as an optical lens does for light. Typically, it consists of small feed antenna such as a patch antenna or horn antenna, which radiates radio waves with a piece of dielectric or composite material in front, which functions as a covering lens to collimate the radio waves into a beam. Conversely, in a receiving antenna, the lens focuses the incoming radio waves to the feed antenna, which converts them to electric current, which are delivered to a radio receiver. They can also be fed by an array to feed antennas called focal plane array or FPA to create more complicated radiation patterns. To generate narrow beams, the lens must be larger than the wavelength of the radio waves, so the lens antennas are mainly used at high frequency end of the radio spectrum, with microwaves and millimeter waves, whose small wavelengths allow the antenna to be a manageable size. The lens can be made of dielectric material like plastic or a composite structure of metal plates or waveguides. Its principle of operation is the same as an optical lens. The microwaves have different speed or phase velocity within the lens material than in air, so that the varying lens thickness delays the microwaves passing through it by different amounts, changing the shape of the wavefront and the direction of the waves. Microwave lenses can be classified into two types by the propagation speed of the radio waves in the lens material. First is the delay lens antenna and the fast lens antenna. Delay lens antennas, also known as dielectric lens antennas, are those where the traveling waves are delayed by the lens media. The lens in this case is usually made up of polystyrene or lucite and polyethylene. These types of antennas are usually used microwaves and wave frequencies, as for frequencies less than 3 GHz, they become heavy and bulky. The index of refraction is greater than 1, so the path length is increased by passing through the lens medium. This is similar action of an ordinary optical lens on light. Next is fast lens antennas, in which the microwaves travel faster in lens material. In this type of radio waves travel faster in the lens medium than in free space, so the index refraction is less than 1. So the optical path length is decreased by passing through the lens medium. This type has no analog in original optical materials. It occurs because the phase velocity of radio waves in waveguides can be greater than the speed of light. Since the thicker parts of the lens decrease path length, a concave lens is converging lens, which focus radio waves, and a convex lens is a diverging lens, the opposite of the ordinary optical lenses. Lens antennas have similarities to parabolic antennas and are used in similar applications. They are used as collimating elements in high-gain microwave systems such as satellite antennas, radio telescopes, millimeter wave radar, and are mounted in apertures of horn antennas to increase gain. So that is all. Thank you and good day.